Okay, now let's look into NOT gate. This is the diagram of a NOT gate, a triangle and a circle at the end. So, what a NOT gate does is, it inverts the input. So, if the input is 0, we get 1, or if the input is 1, we get 0. This is a Boolean expression of a NOT gate, y equal to a bar. A bar means negative of a. Now let us look into the truth table. A being the input, if A is 0, the output Y will be 1. When the A is 1, the output Y will be 0. So, this is the truth table of NOT gate. Now, let's look at the applications of NOT gate. As a first application, let's learn about the ring oscillator. So, a ring oscillator has odd number of NOT gates, and each NOT gate has a propagation delay of Td. That is, when the signal travels from point A to point B, it has a delay of Td. Okay. So, suppose if the signal is 0, the initial signal is 0, then at point A, we have 0. When it travels from A to B, the signal changes to 1. And there is a time delay of Td. And when it travels from B to C, the signal again changes to 0. There's a propagation delay of Td. And again, in the third NOT gate, when it travels from point C to point D, it becomes 1 again with the propagation delay of Td. So we get the output. When we get the input 0, we get the output 1. So now we have 1 here. So this is given as 1. So 1 travels all the way to A. So A will be 1. After a time delay of Td, it will be 0 at the point B. And again after a time delay of Td, it will be 1 at point C. And again it will be 0 at point D after Td. So this will be 0. We have the output 0. We gave the input 1 and now we have the output 0. And in this feedback loop, it gets 0. So again at point A, we have 0. After Td, we have 1 at point B. After Td, we have 0 at point C. And again after Td, we have 1 at point D. So the output is 1 again. And it continues. Let's complete the rest of the table. It is 1, 0, 1, 0. So if we give the input 1, we get the output 0. If we give the output 0, we get the If we give the input 0, we get the output 1. So let's complete this in this graph. In the initial cycle, from 0 to Td, it was 0. Just a second. That was 0. And then from 0 to 1, the output was 0. Even though the output here was 0, even though it became 1 here, it did not reach the output terminal. So it is 0 there. So after 2 Td, it is again 0. After 3 Td, let's see, after 3 Td, it's again 0. After 3 Td, we got the output as 1. Okay. And after 4 Td, that is in the next cycle, here we got 1, and then here it is 0, 1 and 0. But the output after 6 cycles is 0. So we got after 4TD plus 1, 5TD plus 1, after 6TD, it became 0. And again, after 6TD, we reached this cycle. Here it was 0. And then after 7TD, it was 1. And then 0 and 1. But the output remained 0. So it remained 0. And then it goes to 1. So this is the oscillation we get from a ring oscillator made up with NOT gates. Now we know that one cycle, okay, this is one cycle consisting of a crest and a trough. One cycle, the time period is 6TD. That is, time period of T is 6TD. And that is 2NTD, where N is the number of NOT gates. And when we calculate the frequency, F is equal to 1 by T, and that is 1 by 2NT. Now, let us look at the second application, that is NOT gate as a bistable multivibrator. A bistable multivibrator has two stable states, 0 and 1. So, if we give the input 0, it should stay in that stable state 0. If we give the input 1, it should stay in the stable state 1. So, let's look at the implementation. Like the last circuit, it has an input, it has a feedback, but in the ring oscillator, we had odd number of NOT gates, but in the bistable multivibrator, we have even number of NOT gates. We have 2 NOT gates here, and the propagation delay of each NOT gate is TD. So let's see. Here we gave 0 as the input. So it comes here, and it becomes 1 here, and it becomes 0 here. So if the input is 0, the output will be 0. Now let's see. Let's take another let's take another input 1. If we give 1 comes here. After the first NOT gate, it becomes 0. And after the second NOT gate, it again becomes 1. So if we give 0, it stays 0. If we give 1, it stays 1. Now, let us look at the third implementation of the NOT gate, which is the buffer. What the buffer does is, it gives the same input. That is, if we give 0, we have to get 0. If we give 1, we have to get 1. The difference from the bistable multivibrator and buffer is that in the buffer, we do not have a feedback. It is simply 2 NOT gates connected together. 2 or even number of NOT gates connected together. So here, let's see the implementation. Here, if we give input as 0, here it will be 1, and the output comes as 0. If we give the input 1, this would be 0, and the output comes as 1. So this is the NOT gate as a buffer.